Section 7.6, variation. Alright, in this section we kind of switch gears a little bit and look at different kinds of variation which don't necessarily have anything to do with the rational expressions, but they are going to be equations that we're dealing with and having to solve. The first type of variation we're going to look at is called direct variation. Direct variation really is just a case when you have a linear equation. Okay, but direct variation is a situation where we're relating two different things, two different variables. So we say y varies directly as x if we can write an equation of the form that y equals some number k times x. And we call this number k, this value, the constant of variation. Technically it's the slope. It's the number being multiplied by x when we have the equation solved for y. We call it direct variation, and we say that y varies directly as x because as x values increase, the y values, the corresponding y values are increasing as well. As our x values decrease and get smaller, our y values decrease as well, corresponding to those x values. So that's why we call it direct variation. The y values are directly related to the x values. So an example, a real-world example of this would be the cost of filling a tank of gas. That varies directly with the number of gallons that you need. So if you think about it, the more gallons you need, the more it's going to cost you to fill a tank. The fewer gallons you need, the less it's going to cost you to fill the tank. So if we have a situation where gas is $3.75 per gallon, okay, we can look at this as, well, we have the cost of filling your tank. We're told that varies directly with the amount of gallons needed. Well, that means the cost is going to equal some number times the gallons needed. Well, that number is going to be how much we have to pay per gallon. So the cost is going to equal the price per gallon, okay, whatever you're paying per gallon at the pump, times the amount of gallons needed. Okay? So in this case, our K value is the price per gallon. So in more of like a formula setup with variables, we could say the C for cost is going to equal some K value, which in this case is $3.75, times G for gallons. Okay? Or keeping it true to form as y equals kx, we could write it as y equals 3.75x. If you want to write it in y and x form. But either way, in either case, the slope, the value we're multiplying by our independent variable, is our constant of variation. Okay. So y equals k times x. In this case, our k value is 3.75, the cost per gallon. Alright, so there's just an example of when we have direct variation, but now we're going to actually kind of try to apply it and look at some examples where you have to find the constant of variation and where you need to solve the equation. So, finding the constant of variation and the equation, the direct variation equation. So Hooke's law is a theorem or a law that we use in physics. It states the distance a spring will stretch varies directly as the force applied. If a force of 150 newtons stretches a spring 8 centimeters, how much will a force of 400 newtons stretch the spring? Now, direct variation is technically just a situation involving, it's a proportional situation. So you could always, with direct variation, you can handle these all with a proportion, but the ones that are not direct variation we're going to get into, you cannot set up that way. So I just want you to get in the habit of writing the equation. So first things first, we have the sentence, the distance that the spring stretches, okay, it varies directly as the force applied. So that tells us the distance is going to equal some K value times the force, just because the way it was worded. Okay. Then we want to plug in whatever we were given as values to find our K value. Okay. plug in the given values to find k. Alright. So, we were told in the next sentence, if a force of 150 newtons stretches a spring 8 centimeters. Okay, so let's plug that in. The distance that it was stretched was 8 centimeters, and that was stretched by a force of 150 newtons. So the 8 centimeters equals some k value times a force of 150. Okay. Well, to solve that for k is a pretty basic equation. Just divide by 150 on both sides. Okay. And dividing by 8 by 150, we could reduce that to 4/75. I don't even know what fraction that gives us at this point, or what decimal that gives us. For some reason, I kept it in my notes as a fraction, so I'm thinking my math lab is going to want you to keep that as a fraction. So 8 over 150, or reducing that to 4/75. Okay, that's our k value. So in the problems that ask you for your constant of variation, that's all you have to do. Find that k value right there. That's your constant of variation. So you cannot use the proportion. If you did this, actually solved the rest of the problem, which we're about to do, you could use a proportion to find how much a force of 400 newtons will stretch the spring, which we're about to do now. But doing the proportion will not find you the constant of variation, the k value. So you have to do it this way. Even if you have a direct variation problem, you have to do this because you're going to have to find a k value in most of these questions. Okay. So there's our k value, but now we need to go back to the variation equation and plug it in. Okay. So let's kind of bring that over here. Our variation equation was that the distance equals some k value, which we just found, 4/75, times the force, kf. Again, there's our variation equation. So now we're trying to make a prediction based on what we've just found. We know what the k value, that's always going to be the determining factor in each situation, will be 4/75. So how much, excuse me, how much will a force of 400 newtons stretch the spring? So now that's what we're going to check. We're going to put in a force of 400 newtons and see what distance it would stretch it. So the distance is going to equal 4/75 times the force, which we're going to go with a force of 400 and see what that gives us. And that ends up giving us a distance of 1600 over 75. But again, a distance, I don't know why you would keep that as a fraction. So let's convert that. Dividing, you'd get a decimal of 21.3 repeated. And we are dealing in centimeters. Okay, so that's how far it would stretch at 400 newtons of force. You don't need to know what newtons are. It's just a physics term that a newton is a certain amount of force you apply on an object. So I don't really exactly know how much 1 newton would be, what to compare it to, but again, that's not something you really need to know for this class. Alright, so that's direct variation. We still could have other situations that are direct variation, but they might not be as basic as a variable equaling k times another variable. And we're going to come across that in our next example. So let's flip to the next page. And we have an example that says, the distance an object falls varies directly as the square of the time. That word square is going to mean we have to square the time in our equation. So let's handle this piece by piece. So, or we can finish it. If a skydiver falls 64 feet in 2 seconds, how far will they fall in 9 seconds? So this is going to be one because we have the square of the time. A proportion will not work here. It's not proportional when you have something to the second power. So again, let's take what we know. The distance an object falls, the distance varies directly as the square of time. So what that means is we can set up an equation that the distance is going to equal some k value times the amount of time, but squared. Okay, that's what it means when it says the square of the time. So we can then, take the next sentence and solve this, like plug in our values that they give us, and then solve for k to find our k value. So if the skydiver falls 64 feet in 2 seconds, that's all we need in order to solve for k and find our k value. So he fell 64 feet, that's our distance, in 2 seconds time. So k times 2 seconds squared. Okay. So squaring 2, we'd get 4. So 64 equals k times 4. And then dividing on both sides by 4. We get that k equals 16. So if they ask you for the constant of variation in this problem, it would be 16. Okay. But that's not really what the problem's asking. We have to use that to make the prediction of how far the skydiver will fall in 9 seconds. Okay. So we want to come back here and go back to our equation. Our distance is going to equal the k value, which we just found was 16, times the time squared. Okay. So there's our variation equation. And it's direct variation, but it is a direct variation with something squared. So in 9 seconds, what distance will they fall? So let's reevaluate this equation to find the distance equals 16 times a 9-second fall for our time. So 9 squared. Okay. So squaring 9, we get 81. So our distance is going to be equivalent to 16 times 81. And that will give us 1,296 feet. Okay. So 1,296 foot fall is how far the skydiver would fall in 9 seconds time. Okay. So it was direct variation, again, because we had a variable time equals k times another variable. The second variable was a squared variable. So it still works out that as time increases, the distance increases. Okay, the longer the time, the farther that person would fall. The shorter the amount of time of the sky fall, the shorter the distance he'd fall. So it's still direct variation. It's just the distances are increasing pretty quickly as time increases because the time is being squared. Okay. So there's direct variation. Enough examples there. We're next going to look at inverse variation. So direct variation, we said, as our x values get bigger, our y values get bigger. As our x values get smaller, our y values get smaller. Inverse variation is going to be the opposite. We say that y varies inversely as x, first of all, if we can write an equation of this form. See, direct variation was direct and to the point. It was y equals k times x. It was directly across. That's how I usually remember it. Okay. Do you see how this equation is different now? We have y equals our k constant of variation over x. It's the inverse. You end up flipping, and having to put the x on the bottom of a fraction. So hopefully that's an easy way to remember it. Direct variation is directly across, straight across an equal sign, y equals k times x. This isn't so direct anymore. We have y equals k over x. And what it means now is our x values, as they increase, our y values actually decrease. They kind of work inversely of each other. As our x values decrease and get smaller, our y values increase. So it might be hard to think of an actual example of this, but I have one here in the notes, a real world example. Let's look at this. Okay, and that's of a trash compactor, dealing with how much pressure and how much volume is actually taken up inside of the trash compactor. So the volume is pretty much how much space the trash is taking up inside the trash compactor. The volume varies inversely with the pressure. You think about it, the more pressure you're pushing down on the trash, the less space it's taking up. But the less pressure you push down on the trash, the more space that trash is going to take up. And so when we try to set up the equation, if we said volume varies inversely, that means volume is going to be equal to some constant K, some constant of variation, over the pressure. Okay. So there's our inverse variation type of an equation, some K value over the pressure. Okay. So let's see how we can apply this to an example. If 20 pounds of pressure results in 36.5 cubic inches of trash, how much space will the trash take up with 30 pounds of pressure? All right. So we have our formula is that the volume equals K over P. We can use V and P to shorten this formula. So volume equals our constant of variation K over P, pressure. Okay. We know that, from the situation they give us, 20 pounds of pressure results in the trash taking up 36.5 cubic inches of space. So the volume is the 36.5 cubic inches. We always just write volume in some sort of units cubed, units to the third power. That has nothing, the cube has nothing to do with the equation. So that's going to equal K over the amount of pressure that it needed to get that size of 36.5 cubic inches, and the pressure was 20 pounds. So we're going to have 20 down there. So this equation now, in order to solve to find what is our K, our constant of variation, well, if we're doing K, taking K and we're dividing by 20, to get rid of that 20 we would want to multiply. So this is kind of like those rational expressions. We're multiplying by the LCD. Well, if there's only one denominator, the lowest common denominator would be 20. So multiplying by 20 would cancel it out there on the right hand side, but we also have to multiply by 20 on the other side of the equation. Okay? So times 20 here, times 20, again will cancel, and we have to do 20 times 36.5. Okay. And when we do that, we get that K equals 20 times 36.5 should give you 730. Okay. So now we have the K value to put into our equation. So our volume is going to equal 730 over the pressure. And we need to reuse this equation to now make the prediction: how much space will the trash take up with 30 pounds of pressure? Okay, so how much space with 30 pounds of pressure? So we can take that over here. How much volume is how much space it will take up. If we have our K value 730 over the pressure, which we're saying 30 pounds. And if we divide 730 by 30, we get that the volume is equal to 24.3 repeated. and that's in cubic inches of space. Okay, so 24.3 repeated cubic inches. So you see we had 20 pounds took up 36.5 cubic inches. When we increased the pressure, we actually got a smaller volume, which would make sense. You think you push harder down on a thing of trash, it's not going to take up as much space. So that's inverse variation. Okay, the more pressure, the less space it takes up. The less pressure you're pushing down, the more space it takes up. All right, let's go to the next page. We have another example of inverse variation. So here we have that the weight of an object varies inversely as the square of its distance from Earth. Okay? A space shuttle's orbit positions it 4,090 miles from Earth when closest and 6,700 miles when furthest away. If an astronaut weighs 57 pounds at the 6,700 mile mark, how much does he weigh at the 4,090 mile mark? So this sounds like a lot of information, a lot to kind of dig through, and we're going to do that. So, taking a look at this, first sentence. The weight of an object varies inversely as a square of its distance. So the weight varies inversely as the square of distance from Earth. Okay? So that right there tells us we're going to have that the weight is going to equal, it's an inverse variation, so some k value over the distance, but it's the square of the distance. So distance squared to the second power. Okay. So we can think of this as W equals K over D squared. As our formula. So now let's fill in some piece of information we're given. This sentence isn't really necessary. The last sentence, if an astronaut weighs 57 pounds at 6,700 miles. So the weight is 57 when it's 6,700 miles from Earth. So let's fill that in. The weight, 57 equals K over the distance, 6,700 squared. Okay. And then we can solve for K. So what happens here is if we take 6,700 and square it, we're going to get some big number, but then we're going to have to multiply by that number on both sides so that it would cancel out here, and we'd have K by itself. Okay. So technically to get K by itself here, we'd have K equals 57 times that 6,700 squared. I'm just going to write it down here like that so we can squeeze it in. Okay, kind of like we did on the last one to get rid of the fraction. I'll just write it in here for a second. We'd have to multiply by 6,700 squared, and it would cancel out there and there. So we have to multiply by that on the other side as well. Okay. So K is going to equal that value. For some reason, I'm just keeping that as 6,700 squared, it looks like in my notes, probably just so that we don't have to take up some huge amount of space. So using going back to our formula, okay, the weight, we have W equals our K value, which I'm just keeping as, for now, 6,700 squared times 57. You could go ahead and evaluate that if you want. I'm assuming maybe it didn't fit on my calculator, or maybe I was just being lazy when I made these notes. Didn't want to write out that large of the number. But then we put it over the distance squared. Okay. So filling in what we know to make our next prediction, how much does he weigh at 4,090 pounds. Okay, so how much is the weight at 4,090 miles? So we can come here and we'll have that W, his weight, is going to equal 6,700 times 57 divided by the distance squared. Here the distance is 4090. We have to square it. And doing that gives you that W equals about 153 pounds. Okay? If you take 6,700 and square it, multiply that by 57, and then divide that by 4,090 squared, should give you about 153. So I'd make sure you can do that on your calculator. Looks like my phone's going to die, so I'm going to grab my charger, and I'll be right back. Alright, so hopefully you were able to confirm that using your calculator. This doesn't really help if you can't do it and you're just reading my notes or watching my notes. Alright, so now we're plugged in so my phone won't die and our notes can continue. We have a third kind of variation, and it's not really a different kind, it's just joint variation, meaning we're going to use essentially it's a direct variation but with more than two variables. It adds an extra variable in there. So joint variation, we define it as a joint variation situation is when we have y varies jointly with x and z, meaning y is going to equal some k value, the constant of variation, but not just times x times another variable z. So when y is affected by two other variables, that's when we have a joint variation situation. So when one thing is affected by two other things, that is. An example of that is simple interest. Okay, the simple interest formula is that the interest that you earn on, when you have money in a bank, or the interest that is earned when you're in debt and owe money to a credit card, something like that, it varies jointly with the interest rate and the amount of time. So both the interest rate and the time affects how much interest you have to pay. So it doesn't just depend on one of those variables, it depends on both. So because it says interest varies jointly with those two things, so interest varies jointly with the interest rate and time. That tells us we can set up an equation of the form the interest earned is going to equal some k value, our constant of variation, times our interest rate, times the amount of time that we've had money in the bank to earn interest or been in debt to be having to pay interest. Okay? So in this case, the constant is the constant value k. This happens to be if you know the interest formula, simple interest formula, this happens to be the principal, which is how much money you put in the bank to begin with, or how much money you owe to begin with. So principal is how much money that you put in to begin with. As you may know, the simple interest formula is I equals PRT. So the interest earned is equal to P times R times T, principal times rate times time. But that principal, the amount, that's going to be your K value in this case. So let's take our formula, which we will call I equals, I guess we call it P times R times T. Okay. And let's make some calculations here. An investment earns $100 interest at 5% rate for 2 years. Okay, so the interest was $100. We don't know the principal here, the principal amount. 5% rate is 0.05 times time was 2 years. Alright, so there's our formula. We can use that to solve for P and find what P is. In other words, our K value. But we're going to find how much do we have to invest initially then. So 100 is going to equal 2 times 0.05 is going to give you 0.01. So then to solve for P, we would divide on both sides by 0.01. Oh, sorry, I wrote that wrong. That was supposed to be 0.1. Erase that. .1 and 0.1. Okay, so we divide by 0.1, we divide by 0.1, we get that our P, our principal amount, was $1,000. Okay. But that's not what the final question's asking you. We are being asked to find, how much the that same amount of principal, 1,000, will earn at 4.5% for 3 years. So the same principal, $1,000, earn at 4.5% for 3 years. Okay. So we're going to use that the interest formula equals the same P, $1,000, times the rate times time. Okay. So we're going to evaluate for 1,000. Our interest rate now is 4.5%. We need to convert that to a decimal. So 0.045 is what 4.5% equals, times the amount of time, which is 3 years. Okay. So now we can just multiply straight through and evaluate that expression. We get that the interest earned, 1,000 times 0.045 times 3 gives us $135. Okay. So that is a joint variation situation. It essentially is direct variation in the sense that it's straight across, but it's not direct because the interest, like in this case, isn't directly related just to the rate, or it's not directly related just to the time. It's related to two variables. So, but they all kind of work the same. You have to solve for the K value, and then plug that back into the equation and fill in the information they give you to find out, to make some sort of prediction. Okay. We have one more example on the last page, and this is one more kind of variation, and it is called combined variation. And it's just like it sounds. When you use combined variation, it's just combining the two types of variation we've already used. So you could have combined variation where you involve direct and inverse variation together. Okay. This is probably pretty tricky to think of an example when that would be the case. One example of that is when you take your body mass index, your BMI. Okay. Gives you an idea of about how healthy you are. So, body mass index, or BMI, it varies directly as an individual's weight and inversely as the square of their height. A man weighing... Okay, well, before we even get into the specifics, let's come up with the basics of the equation. Okay. So body mass index varies, so BMI varies directly as the individual's weight and inversely as a square of their height. Okay, that sounds pretty crazy. Let's come up with a formula for that. So BMI, it varies directly, so that's where we have K times some variable, directly across. So K times their weight. Okay. But then also inversely, that's where we have K over and divide it by something. So we put it over the square of their height. So we put it over the height squared. So there's our formula. To put it in short, we can use this as BMI equals K times W over H squared. Okay. So filling in the pieces of information they give us, the man weighs 118 pounds, 64 inches tall. It's a pretty skinny man. He has a rounded BMI of 20. I guess BMI is something you typically round. So let's plug that in, and that can help us find our K value. So his BMI rounded was 20 equals K times the weight, 118 pounds, over his height squared, 64 inches. I guess when you do height in this formula, you want to use inches, so 64 squared. In order to now solve this equation for K, we would need to first multiply by 64 squared on both sides, because that'll cancel out our fraction. Excuse me. And again, you could evaluate 64 squared. I think I'm just doing it now like this to save some space. Okay, so multiplying by 64 squared will cancel out the fraction. Over here, 64 squared times 20 would give you 81,920. That's going to equal, now we just have K times 18, since we canceled the fraction. So solving that, we'd want to divide by 118 on both sides. And we get a K value of about approximately 694.24. Okay. So we want to take this and now use that in our formula. So our BMI is going to equal our K value, 694.24, times our weight, all over our height squared. So take the rest of the information they give us now. The BMI of a 165 pound, 70 inch man. So the BMI is going to equal 694.24 times his weight, which is 165 pounds, all over his height squared, so 70 squared. And evaluating that, 694.24 times 165 divided by 70 squared gives us a rounded BMI. So BMI approximately of 23.38. I rounded to 2 decimal points. I think BMI typically you round to the nearest whole number, so I think it'd be 23. I guess see what my math lab tells you to do on that problem. And that is it for variation.